Hey guys, welcome to this video over insertion and selection sorting. I'm just gonna cover both of these types of sorting algorithms. Both will be in Java, and I'll just sort of explain the logic behind it, the time complexities, and just how it works in general, I guess, along with its advantages and disadvantages. So let's start with insertion sorting. And the first thing we should cover is that it just takes an array, and the way I have set it up is I have a void method, which I later print with my driver method right here. And so, yeah. Alright, so right here, int array, right? We just named my parameter array. We're just going to be sorting ints in this case. Uh, so we just made it easier. We just stored the array length as int n so we can use it more easily. And we start with our for loop. And if you notice, the integer starts at index 1. So that already means that like we're sort of skipping past the first element or the 0 index element because we're looking one space ahead of it. We're just doing I plus plus basically. That's the synonymous meaning. Uh, I created an integer called key, and that'll store the current array element. And I also created another int variable which is equal to j, and it's just equal to the index value minus 1. So here's my while loop. Let me just go through the code first, and I can sort of explain the logic behind it. So I have my while loop, and as long as my j is greater than or equal to 0, which means that this should work for the entire array, and array of j is greater than key. So as we saw, j is one index less than I. So as long as, and key is just I, so j is one less than I. So as long as if j is greater than I, then what we want to do is we sort of want to swap the two elements. So right here, we'll pick up the value j plus 1 is basically I, and we'll turn that into array j. J is equal to j minus 1 or j minus 1. And then after we do that, array of j plus 1 is equal to key. This all it does is just swap the two elements, assuming that the index behind it is greater than key. So let me use an example. So here's my integer array, and let's go through this logic. So I'm starting at index 1, so that means the second element right here, which is 11. So what I'm basically doing right now is I'm going and checking if array j is greater than key. So I'm going to go check the element behind it, and if it's greater, 19 is greater than 11, all I'm doing is swapping these two, so that the new array is now just the swapped version, which is 11 and 19. And I'll do this with these two as well. As you can see, 19 is obviously greater than 3, so I'll just swap the two. But now we build upon the logic in the sense that we can't just leave it here anymore because now this is unsorted. So because of this while loop we have here, while j is greater than or equal to 0, means that it'll look back all the way, meaning all the elements from the 0th element to j will all be looked at. So because that's basically what j is. J is equal to the index that we had minus 1. So the index we had was originally 2, but now it's just 1. And as long as j is greater than or equal to 0, according to our while loop logic, and we keep subtracting 1 from it, it'll check these two now. And what it'll do is it'll see, oh, there's another problem, we have to swap them. And it will swap them. And it'll keep doing that throughout the entire array until it is fully sorted. And here I've just created my object, and I'll just call the sort method, and I'll print it. I just printed it using a normal for loop. You could have done a toString method, whatever you wanted to do. But So some advantages of an insertion sort is that if the array you pass on is already fully sorted, it'll go through the loop just once, meaning it'll go in O of n time. That's pretty good because that's just linear time. And most of the times with sorting, it's almost impossible to get that. But insertion sorting made that a lot easier. So now, some disadvantages it has is that it doesn't work well with big data sets, and it'll just take too much time because the worst time complexity it has is O of n squared, which means, you have to take one array and then it'll sort of go like two arrays at the same time. It's hard to explain, but basically, if you give it a large data set, it'll take much longer than with the smaller data set. Usually, you would think that'd be pretty common with all sorting algorithms, but that's actually pretty wrong. And there are some sorting algorithms that are designed for larger data sets and can do much better with those. So if we look at selection sort, then we can see that it's just a void method, right? And so the parameter it takes on is an integer array. Same thing as last time, we just make the int n is equal to the array length. And then we start with our for loop right here. So this time we start with the index starting at 0, and we just have to make sure we don't run into a runtime error. So then, we just have to make sure that's there, and I++. So it becomes a little bit more complicated than a insertion sort, but here's where the majority of the logic is. What we want to do is we want to iterate through the entire array and find the smallest value there is. Therefore, we just create a min index sort of variable. And we're just going to iterate through the for loop. And here, remember, j is I plus 1. So we're sort of starting at the next index, to say. And our if statement is just if array j is less than min index is now equal to j. Basically, all we're doing is we're iterating through the entire for loop, and we just want to find the smallest element there is. So here's our example. So let's say our for loop starts from here, and 25 is j, right? So we're comparing 64 and 25. Well, obviously, 25 is smaller than 64. So our min index will now be stored as j, which is 25. So our new smallest number is 25, and this process will repeat until we get all the way down to smallest value, which is just 11. And then once we come into 11, what we do here is we create a temporary value, and I just named it temp, and we do array of that smallest value, and we move it all the way to the front. Well, not all the way to the front, but we will push it to where we start from. And where we started from was initially 0. So yes, in this first case, we will move it all the way to the front. And we just swap them. We swap their two positions. So in this first pass, it'll start from 64. It'll look through the entire array, and it'll see 11 is the smallest number. And it'll just directly swap the two. Nothing in between. It'll just directly swap the two. That's what it does. And then it'll do it again, but this time it'll start at this index, because it already knows 11 is the smallest number, so we don't have to worry about that anymore. And it'll go through the entire thing. It'll see that 12 is the smallest number, and it'll flip them again. And it'll keep doing this until the array is fully sorted. And yeah, so this time complexity, its worst time complexity is O of n squared, and its best time complexity is also O of n squared. So, I mean, if you want to use the better one, I would usually go with an insertion sort. There are a few advantages of selection sorts over insertion sorts, but not many people care for it because the time difference is just so minuscule, it doesn't even matter anymore. I just printed out the same way, created the object, and I just sorted it. Let's do some examples. So, also sort of the same thing with selection sort. Some advantages is that it works really well with a smaller data set, meaning with this small array, it'll easily be able to do it quickly. But if I made the array much bigger, or gave it a much bigger data set to like iterate through, it would take a much longer time. And there are other sorting methods like quicksort, bubble sort, that will be able to do these quicker. So the reason that beginners usually, I recommend beginners should learn these two, are because they're much easier to understand than the others, and these are also great starting points to learn some advantages and disadvantages of sorting in general. So let's actually quickly run some. Uh, let's quickly run some examples right now. So what I'm going to do is I'm just going to compile my insertion sort code, and I will run it. Insertion sort. Alright, so as you can see, it goes in ascending order. If we wanted to go in descending order, we would just have to change this in the while loop, and yeah, we would just have to change it in the while loop, and that should do it. But let's try to make this array a little bit more complex. Obviously, all of these values have to be integers, so let's just make it a little crazy. And yeah, and it should still be able to sort this accurately. We still need to compile it, and yeah, it's still in ascending order. Perfectly done. As you can see, obviously, when I clicked the enter button, it didn't take that much time for it to load, but obviously, when you get into more advanced computer science, you will realize that time complexity is a really big factor in a lot of algorithms and logic. So it's important to take note of that. So this is obviously an unsorted array. If I were to give it a much simpler one, like maybe this or something, where it's already sorted for me, I could just compile it, and you guys probably won't see the difference, but that was faster by a good amount of nanoseconds actually on that pass, because it only iterated through the entire array once, and it was able to get it in perfect sorted order because it was already sorted. Now going to selection sort, on the other hand, we can run this. And remember, the time complexity for selection sort is that it'll be O of n squared no matter what. So no matter what you do, it'll always just be a little slower than a perfect insertion sort. So as you can see, it's fully sorted it, but it did take a few passes. It had to go iterate and then iterate again, and yeah. It just doesn't have to iterate at the end because there's nothing after that element. So yeah, you could say there was maybe 3-4 passes in that whole array. 4 passes in that array, while insertion sort was only 1. So you can obviously see that there was a huge difference. In this array is like nearly sorted. So if I were to just make this like 21 or something, it would still take the same amount of time as an unsorted array. So yeah, right here, it took the same amount of time as this one and this one. This array was already sorted. This was an unsorted array, so you know it takes the same amount of time. So if you want to, if you guys want to understand, a really good tip is that when you're using small data sets and you're asked to choose between these two, I would usually choose insertion sort, just because of the time complexity. But usually, you won't be given a sorted array by itself, but if there is a chance that you might, in a any scenario, honestly, you might as well go choose the insertion sort, because there are really little benefits with the selection sort over the insertion sort. So yeah, thank you guys for watching. I hope you guys enjoyed this video, and please subscribe.